Hello friends, welcome to the channel Gaivi and Salkai. Continuing with the pharmacology of diuretics, today we are going to discuss about potassium sparing diuretic. First of all, let's break this word. Potassium sparing and diuretic. So, diuretic are the drugs which cause a net loss of sodium and water in the urine. We know actually there is loss of sodium and water just follows it. Loss of sodium in the urine is known as natriuresis. So diuretics are also known as natriuretics. Potassium sparing. It means these drugs conserve or preserve potassium inside the body by decreasing potassium excretion. Potassium excretion in the urine is known as kaliuresis. So we can say that these drugs decrease kaliuresis. We will talk about their potassium sparing action later in the video. Site of action of potassium sparing diuretic is distal tubule and collecting duct of nephron. Now, we must understand the normal sodium reabsorption that occurs at collecting duct and distal tubule, because when this sodium reabsorption is inhibited, increased sodium passes in the urine and we get our desired diuretic action. Sodium absorption at the distal tubule and collecting duct is physiologically under the influence of aldosterone. That is, it is normally controlled by aldosterone in the body. Aldosterone is a potent mineralocorticoid hormone which is secreted by granulosa cells of adrenal cortex, and its major function is as follows. First, it helps in sodium reabsorption. Second, it promotes K plus excretion or secretion into the lumen, and third, H plus excretion or secretion into the lumen. Now let us observe a single cell present at the distal tubule or collecting duct. This cell is known as principal cell. Aldosterone enters the principal cell from interstitial side through basolateral membrane and combines with an intracellular receptor known as mineralocorticoid receptor. The mineralocorticoid receptor aldosterone complex translocates to the nucleus and promotes gene-mediated mRNA synthesis through transcription. The mRNA then directs synthesis of aldosterone-induced proteins through translation. The AIPs is the major protein responsible for all aldosterone actions. It helps in the translocation of Na plus K plus ATPase and sodium channels from the cytosolic site where they are synthesized to basolateral membrane and luminal membrane respectively. We can therefore say that AIPs are responsible for the proper functioning of sodium potassium ATPase and sodium channels. We will now see the function of sodium potassium ATPase. It promotes efflux of 3 sodium ions for every 2 potassium ions influx into the cells. This mainly serves two purposes. First, it decreases sodium concentration inside the cell, which creates a sodium gradient on the luminal side. That is, increased sodium on the lumen side and decreased sodium inside the cell. This results in easy entry of sodium into the cell through sodium channels. These channels are also known as amiloride sensitive sodium channels and renal epithelial sodium channels. And the second, increased K plus concentration inside the cell. So, principal cells have high intracellular potassium concentration, which causes easy secretion of K plus into the lumen through K plus channels. Also, some amount of K plus efflux is there into the interstitial space through leaky K plus channels. For easy functioning of Na K plus ATPase, because it requires adequate amount of K plus at the interstitial site of the basolateral membrane. We can thus see sodium entry occurs at the luminal side through sodium channels along the gradient created by sodium potassium ATPase present at the basolateral membrane. This sodium is transported to the interstitial side by NaK plus ATPase, and this is how the sodium is reabsorbed. Now, the sodium entry excludes chloride or any other anion present at the luminal side. This causes development of partial depolarization on the luminal membrane. Now, there is formation of negative lumen transepithelial potential difference due to increased concentration of anions on the luminal side of the membrane. It is approximately equal to minus 15 millivolts. Now, this is a very important point, that development of this negative lumen transepithelial potential difference is responsible for the proper functioning of K plus channels and H plus channels. So, sodium entry causes development of negative lumen transepithelial potential difference, and this is responsible for secretion of K plus into the lumen by K plus channels and secretion of H plus into the lumen by ATP driven H plus pump. By this information, we now understand that without sodium reabsorption, potassium and H plus secretion cannot take place. And also we can understand that if sodium reabsorption increases, luminal membrane is depolarized to a greater extent. There is increased formation of negative lumen transepithelial potential difference, and more K plus and H plus is secreted into the lumen. It is also important to notice that the source of H plus inside the principal cell is H2CO3 through an enzyme known as carbonic anhydrase, and decreased activity of this enzyme causes less H plus inside the cell and less H plus secretion. I shall talk more about it later in the video. So, whatever we have learned is the normal function of aldosterone, that is sodium reabsorption, K plus secretion, and H plus secretion into the lumen. Two major potassium sparing diuretics are spironolactone, which act at the MR mineralocorticoid receptor, and amiloride, which act at the amiloride sensitive sodium channels. We shall see this later in the video. Let us now try to understand why is there a need for conserving potassium, why a whole new class of drugs is made when we already had significant number of diuretics. The other diuretics such as loop diuretic, which act at medullary part of thick ascending limb of loop of Henle, carbonic anhydrase inhibitor, which act at PCT, thiazides, which act at cortical part of thick ascending limb of loop of Henle. We can see that these diuretics act at such sites in the nephron which are proximal to DT and CD, and they increase the amount of sodium that arrives at the DT and CD region. There is increased sodium reabsorption at the distal tubule and collecting duct compared to normal condition due to compensatory mechanisms. It causes, because we have already learnt that if sodium reabsorption is increased, luminal membrane is depolarized to great extent and there is formation of more negative lumen transepithelial potential difference. This causes increased secretion of K plus and H plus in the urine. Let us understand this with the help of an example. In the normal condition, suppose 100 sodium arrives at the DT and CD region, out of which 40 Na plus is reabsorbed and 60 Na plus is secreted into the lumen as urine. To maintain the charges due to 40 Na plus, 20 K plus and 20 H plus is secreted into the lumen. Now, the second condition in which a diuretic is being used, they decrease sodium reabsorption proximal to DT and CD region, and hence increased sodium now arrives at DT and CD. Suppose in place of 100 sodium, now 200 sodium arrives at this region, and 80 Na plus is absorbed and 120 Na plus is secreted. In spite of increased sodium reabsorption, now in place of 60 Na plus, 120 Na plus is secreted into the lumen. So our diuretic action has been achieved, but it is important to note that now 40 K plus and 40 H plus is secreted into the lumen. This increased potassium secretion in the lumen is the major cause of hypokalemia. Now, an important point for carbonic anhydrase inhibitor. It is important to note that H plus cannot be generated in the principal cells which are present in the DT and CD region, because source of H plus is H2CO3, which is converted to H plus with the help of an enzyme carbonic anhydrase, and this enzyme is inhibited by the carbonic anhydrase inhibitor. So only K plus and no H plus can be secreted. Now in place of 40K plus, 80K plus is secreted in the lumen. So we see that if we take diuretic, loop diuretic, thiazides and carbonic anhydrase inhibitor at similar natriuretic doses, that is if all three of them secrete 120 Na plus, carbonic anhydrase inhibitor causes maximum hypokalemia, that is maximum kaliuresis for the same degree of natriuresis. So we see that there is a problem of hypokalemia with these diuretics, and in order to prevent K plus loss, we must use potassium sparing diuretic. And how potassium sparing diuretic prevents potassium loss, this is discussed with individual drugs. Coming to the classification of potassium sparing diuretic, we have two groups, aldosterone antagonist and renal epithelial sodium channel inhibitor. The first one include spironolactone and eplerenone, and the second one include amiloride and triamterene. It can also be remembered with the help of a mnemonic SEAT, SEAT. The first one is aldosterone antagonist. We will be discussing this considering spironolactone as the prodrug. Spironolactone is a competitive antagonist to aldosterone. It means that it has a similar structure like aldosterone and binds to same site in the mineralocorticoid receptor. The mineralocorticoid receptor spironolactone complex fails to translocate to the nucleus. This inhibits the formation of AIP, aldosterone-induced proteins. Na plus, K plus ATPase and sodium channels are non-functional. There is decreased reabsorption of sodium. This causes no formation of negative lumen transepithelial potential difference, and the K plus channel and H plus pump fails to function. Therefore, there is less K plus secretion and less H plus secretion, and we see that potassium is spared, which was our prime concern. It is also important to note that spironolactone is the only diuretic which acts from the basolateral membrane. All other diuretics, they first come in the lumen and they act from the luminal side. Coming to the uses of spironolactone, it is used for its potassium sparing action. For this, it is combined with a loop diuretic or thiazide to decrease potassium loss. Note that potassium sparing diuretics are not used alone. It is not of high efficacy. If we observe the total amount of sodium being reabsorbed at different portions of the nephron under normal conditions, we find that at PCT there is 65 to 70% reabsorption, thick ascending limb 20 to 25%, DT 8 to 9% and CD 2 to 3%. We see that very small fraction of sodium reaches DT and CD, and preventing reabsorption at this site doesn't make a very big difference in the sodium status of the body. Second use, edema. These decreases sodium in the blood by promoting diuresis. Water content of the blood is also reduced, blood volume decreases, there is rapid mobilization of edema fluid into the blood. It is mainly used in edema due to liver cirrhosis and nephrotic syndrome, because in these conditions there is increased aldosterone levels. It is also used in hypertension because they decrease blood volume, decreases cardiac output and reduces blood pressure. Now here it is important to understand the meaning of resistant hypertension and refractory edema. If we use loop diuretics or thiazides in the treatment of edema or hypertension, the aldosterone levels are increased due to compensatory mechanisms and try to restore sodium levels in the body by increasing its reabsorption. This results in development of refractory edema or resistant hypertension. This is treated by combining spironolactone to loop diuretic or thiazide because they suppress normal aldosterone action. The other use is heart failure. These drugs decrease blood volume, decreases venous return, and hence decreases preload. When preload decreases, heart has to do less work. It is also used in primary hyperaldosteronism known as Conn's disease. As the name suggests, it is a condition where aldosterone is increased. Interactions of spironolactone. Potassium supplements plus spironolactone results in dangerous hypokalemia because both of them increases potassium in the body. Aspirin blocks spironolactone action. ACE inhibitors or ARBs plus spironolactone results in hyperkalemia. Why? ACE inhibitor or ARB are the drugs which block RAS system, renin-angiotensin-aldosterone system. So aldosterone is blocked and spironolactone also decreases aldosterone function. So there is hyperkalemia. Spironolactone increases plasma decoction concentration. Adverse effect of spironolactone. There is a risk of hyperkalemia. It increases testosterone conversion to estradiol. In males, this results in gynecomastia, erectile dysfunction, loss of libido. In female, this results in breast tenderness, menstrual irregularities. Now the second group, renal epithelial sodium channel inhibitors. As the name suggests, these drugs block luminal sodium channels. These channels are also known as amiloride sensitive sodium channels or renal epithelial sodium channels. When these channels are blocked, all the subsequent actions are similar to the spironolactone, absolutely similar. Why? Because in this condition also there is no formation of negative lumen transepithelial potential difference. The sodium channels actually the potassium channels and the H plus pump, they both cannot function, and if they do not function there is decreased potassium secretion and decreased H plus secretion, and we see that potassium is spared, which was our primary concern. The uses of renal epithelial sodium channel blockers are similar to spironolactone, absolutely similar. There is one more use in cystic fibrosis where they increase fluidity of respiratory secretions. Interactions are also similar and they have less adverse effects like nausea, diarrhea, and headache. Thank you for watching. That's all for today. Hit the like and subscribe button and stay tuned for the journey of advanced cognition.